Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Elena Caviglia from University of Leicester. She will talk on two stacks and quotient two stacks, and we thank her for giving this nice talk to us. Please.
Yes, so first of all, thank you very much for the opportunity to give this talk. The talk today will be about part of my PhD project, and I will talk about two stacks. In particular, I will introduce a notion of two stack that is suitable for a triomomorphism from a two category into the three category of bicategories. And then we will see what is the motivating example for me to introduce this notion, that is the example of quotient two stacks. And I will tell you why I came up with this example and what is it. So the talk will be essentially divided in two parts. In the first part, I will recall the notion of site and stack, the usual notion, so the one-dimensional notion. Then we will go one dimension higher and we'll see what is a bi-site. And then we will define two stacks. And we will see that the definition that we give is quite abstract and implicit in some sense. And so the idea is that we can give a characterization of this definition in terms of explicit conditions that are much easier to check when one wants to prove that something is a two-stack. And we will see how to do this. And after that, we will move to quotient two stacks. I will talk a little bit about what I did in the context of sites, so in one-dimensional categories, because I generalized principal bundles and quotient stacks in this context. And then we will move to dimension 2, and I will tell you how I did the same theory, but in dimension 2. And in this case, the objects that we find are two stacks. And that's why I needed this notion of two stack. So let's start with recalling sites. So we will work for now in a category with pullbacks, and we say that a sieve on an object of this category is a collection of morphisms that all have codomain this fixed object, and that is closed under precomposition with all morphisms of C. And another way to see a sieve is as a subfunctor of Ioneda of C. So it is a natural transformation of this form. So with target Ioneda of C with injective components. And the source of this natural transformation assigns to every object of C the set of all arrows in S with domain that object. And then we can define this R of S on morphisms simply by precomposition. And sieves are the main ingredients to define a Grothendieck topology on the category C. And the Grothendieck topology assigns to every object of the category a collection of sieves that we call covering sieves in a way that satisfies three axioms. The first is just saying that if we take all the morphisms into C, this is a covering sieve. The second is saying that if we consider a covering sieve and we pull it back along an arrow of the category, what we get is a covering sieve again. So the topology is closed under pullbacks. And the third axiom is saying that being a covering sieve is a condition that can be checked locally. And this locally is with respect to morphisms in a covering sieve. So this is what this condition is saying. And there is another way to present a Grothendieck topology that uses covering families instead of sieves. And this can be also thought of as a basis of the Grothendieck topology in the same way in which we have a basis of a usual topological space. And we will use this language of covering families a bit later, but our main language is that of sieves. So that's why I presented the definition in this way. And a category equipped with a Grothendieck topology is called a site. And now we want to see what a stack is. And to do this, one ingredient that we need is that of a descent datum. So if we consider a pseudo-functor from C up into cat, a pseudo-functor is just like a functor, but it preserves identity and composites only up to isomorphisms instead of preserving them strictly. And a descent datum on a sieve S for this pseudo-functor F assigns to every morphism in the sieve S an object, W of F, we call it W of F, in the image of the source of the morphism. And then for every pair of composable morphisms, like these ones, I don't know if you can see my pointer, I hope so, where the second one is in the sieve, we have an isomorphism that we call phi fg between the assignment on the composite F composed with G and the descent along G of the assignment on F. And this bunch of isomorphisms that we get for every F and G are compatible in the sense that if we now take a chain of 3 morphisms where the last one is in the sieve, we have a commutative diagram of this form. And this condition is called the cocycle condition, and it relates the isomorphisms for F and G, for H and F composed with G, and F and G composed with H. And this isomorphism on the left of the diagram is a canonical isomorphism and is simply given by the pseudo-functoriality of F. And once we have a descent datum, we can say that this descent datum is effective if we can find an object that we call W, this time in the image of C. So C is the object related to the sieve S. So the sieve S is on C. So we can find this object. And the idea is that this object is able to recover all the local data of the descent datum. So for every morphism F in the sieve, there is an isomorphism between the local data W of F and F star of W. And another way to think of W is that W acts as the assignment W identity of C. So the identity of C is not in the sieve in general. It is in the sieve only if the sieve is the whole unit of C. So there is no W of identity of C. But W kind of acts like W identity of C. And here we can find the compatibility condition that is satisfied by this isomorphism C of F. And this kind of looks like the one of the previous slide, so the cycle condition, if you remember it. I show it for a second. So this condition is really similar to this one. But, and again, this isomorphism on the left is a canonical isomorphism given by the pseudo-functoriality of F. And we can think of this condition as the cocycle condition when the morphism F, the one in the sieve, is the identity of C. even if this is not an actual cycle condition, but that's the idea. And so now we know what it means for a descent datum to be effective, and we can define what a stack is. And the idea is that a stack is a higher dimensional analog of a sheaf. So it will still glue things, but in a weaker way than a sheaf. And we say that a pseudo-functor F is a stack if it satisfies these three conditions. So the first one is that every descent datum on a covering sieve for F is effective. So they are all effective. And the other two conditions put together are saying that F is a sheaf on morphisms. So the first is a condition of gluing of morphisms. So if we have a covering sieve and we fix two objects in the image of C, and then for every F in the sieve, we have a morphism W of F, and these morphisms are compatible in this with respect to composition, then we can find a morphism W from X to Y such that F star of W is W of F. So this is similar to the condition that the effective.
亲眼看见甜甜开水龙头。
Sorry.
刚才亲眼看见甜甜开水龙头。很简单的句，很自然的。
Sorry.
哎，你接到他给他自由了吗？
I am really sorry. I muted the person.
Oh, it's okay. Okay. I just go on. Thank you. So if you look at this condition, this is similar to the effectiveness condition. The only difference is that now we have an equality. Okay, so it's kind of an effectiveness condition, but this time on morphisms. And we also have a uniqueness condition of these gluings. So if we have two objects in F of C and two morphisms between them that agree locally, so F star of W is equal to F star of W prime, then they are equal. So we have these three conditions, effectiveness of descent data on objects and a sheaf on morphisms. And but there is an equivalent way to see a stack. We can okay. There is a useful characterization of the notion of stack that is due to Ross Street. So we have that F is a stack if and only if for every object of the category C and every covering sieve, the functor of precomposition with the covering sieve is an equivalence of categories. And the idea behind behind this characterization is that the right-hand side of this equivalence is the category of descent data, while the left-hand side of this equivalence is equivalent to F of C by Deyon and Alemma. So we are relating F of C to the category of descent data somehow. And so we have that the conditions of equivalence of categories, so the essential surjectivity and the faithfulness, are translated into the usual conditions of stacks. So the fact that this pseudo-functor is essentially surjective is saying that every descent datum with respect to the sieve S is effective. Then the fullness of this equivalence of categories is saying that we have gluing of morphisms, and the faithfulness is saying that we have uniqueness of gluings. And this is really important because this is what we will do one dimension higher for two stacks. So now we can move one-dimensionally. So the setting will be now a 2 category with bi-isochroma objects. And bi-isochroma objects are a 2-dimensional analog of pullbacks. So we will upgrade pullbacks to bi-isochroma objects. And now we need to put a Grothendieck topology on these 2 categories. And we could simply consider a Grothendieck topology on the underlying category of the 2 categories. But this is not something we want to do, because we really want a 2-dimensional topology. And I hope this will be, the motivation of this will be clear later on in the talk. And so what we consider instead is the notion of bi-topology that Ross Street gave for a bi-category, more in general. But here we only apply it to a 2 category, a strict 2 category. So we say that a bi-sieve over an object C is a fully faithful arrow S of this form with target unit of C in this category. And here we have to make some comments about the differences between a sieve and a bi-sieve. So first of all, S is just pseudo-natural in this context. And this means that the bi-sieve is not closed under precomposition on the nose, but only up to isomorphism. And this is the first difference. And then here we are not asking that this arrow is injective on objects. And this is a bit of a problem, because this is what guarantees that we can really speak about amorphism in the sieve. And this is something that we want to do because it's easier to work in these terms. And we are lucky because we can only consider bi-sieves that are injective on objects, since every bi-sieve is somehow equivalent to one that is injective on objects. And for our purposes, is enough to consider the ones injective on objects. So we will always take this hypothesis that we have bi-sieves injective on objects, and so we will be able to freely speak about amorphism in the bi-sieve, also in this 2-dimensional context. And then the last comment is that here we are taking a fully faithful arrow. And in particular, the fullness of this arrow is saying that we are considering all 2 cells to be in the bi-sieve. So we are choosing which cells are in the sieve, but we are not choosing the 2 cells. We are simply taking all the 2 cells. And now Street defines a Grothendieck bi-topology on K as an assignment for every object of K of a collection of bi-sieves that we call covering bi-sieves, in a way that satisfies these 3 axioms that are analogs of the ones that we saw in dimension 1. So the first says that the identity of Yoneda of C is a covering bi-sieve. Again, the second one this time says that covering bi-sieves are closed under bi-isochroma objects. So if you remember, in dimension 1, we had closure under pullbacks. So again, we upgrade pullbacks to bi-isochroma objects. And the third condition is again saying that being a covering bi-sieve can be checked locally with respect to a covering bi-sieve. And so now we say that a bi-site is a 2-category K equipped with a bi-topology. And now what we want to do is we want to give a notion of 2-stack. And the most natural thing to do is to generalize the characterization of stack that we saw before. So we give this definition. If we have a bi-site and a triomomorphism F from K up to bi-cat, we say that it is a 2-stack if for every object in K and every covering by sieve, the pseudo-functor of precomposition with the covering by sieve is a biequivalence. So this is a really natural generalization of the characterization that we saw before. And similar generalization have been done in different contexts. So also the notion of infinity one stack is similar to this one. And also Campbell gave a notion of two stack, but for something that goes from a one category, that has a one category here as source. And this notion is also similar to this one. And that's because this is a very natural way to generalize Street's characterization of stack. But the problem with this definition is that it is really implicit and abstract. And if you sit down and try to prove that a particular triomomorphism is a two-stack using this definition, then this is going to be a nightmare because you need to work with these three categorical objects, three modifications, perturbations, and it's really complicated. And so the idea is that I wanted to find explicit conditions similar to the ones that we have in dimension one that can be easily checked, quite easily checked in practice. And since in dimension one, the idea behind the characterization was the use of the Yoneda lemma, here we will need to use a three-categorical version of the Yoneda lemma that has been proved by Bounet. So if we have a triomomorphism from K up into B cut, actually the theorem of Bounet is slightly more general, but here I'm just writing it in this case because this is what we will need to use. So if we have a triomomorphism, then for every object in K, there is a biequivalence between f of C and this bicategory. So this is exactly the Yoneda lemma, but in the three-categorical context. And the proof of this also gives the explicit biequivalence as it happens in the standard case of the Yoneda lemma. And so the idea is that every object of f of C will correspond to a tree transformation, call it sigma, from Yoneda of C into F. And the component D of sigma will send a morphism F from E to D into F of X. And in an analogous way, we can define explicitly the tree modification that corresponds to a morphism from X to Y and the perturbation that corresponds to a two-cell in f of C. And so using the three-categorical Yoneda lemma, we will be able to give the explicit conditions. So we can start with a characterization, if you want, of two-stack, but a very easy one. So we said that a triomomorphism is a two-stack if for every object the pseudo-functor of precomposition with every bi-sieve is a biequivalence. We can equivalently say that it is a two-stack if for every bi-sieve the precomposition with the bi-sieve precomposed with gamma, which is the biequivalence given by the Yoneda lemma, is a biequivalence. So here we are simply using the 2 out of 3 rule for biequivalences. And then we notice that biequivalence means these 3 conditions. So surjectivity on equivalence classes of objects, essential surjectivity on morphisms, and fully faithfulness on two cells. And these are the 3 conditions that we want to translate into the explicit conditions of a two-stack. So we start looking at the two cells. And we start with the fullness. So the fullness on two cells of the bioequivalence that we have in the definition of two-stack gives a condition of existence of gluings on two cells. And so this is the condition. If we have two morphisms, A and B from X to Y in f of C, and then we assign to every morphism in S a two cell, alpha F, from F star of A to F star of B, and we assign this bunch of two cells in a compatible way that is shown by this equality of two cells. Then there exists a two cell from A to B that recovers locally all the alpha F. So F star of alpha is alpha F for every F. And so this is exactly an existence of gluing conditions, but this time it is on two cells. So instead of having a morphism, we have a two cell, and instead of having a commutative diagram, here we have an equality of two cells. And an analogous thing is what happens with the faithfulness. So this time we get a uniqueness condition for gluings on two cells. So given two cells between A and B that agree locally, so F star of alpha is equal to F star of beta for every F in the bisieve, then we have that alpha is equal to beta. So if we look at these first two conditions that we find and we put them together, this is saying that that the two stack is a sheaf on two cells. And this is a condition that we might expect to find because we have that, okay, a sheaf is a sheaf on objects. Then when we move one dimension higher, we get a stack, which is a sheaf on morphisms. And then here we are moving one dimension higher, and so we expect to get a sheaf on two cells. And this is exactly what we get. So we are happy with this condition. And if we now look at morphisms, we have that the bioequivalence of the definition of two stack needs to be essentially surjective on morphisms. And the essential surjectivity actually gives the condition that every descent datum on morphisms is effective. So what is a descent datum on morphisms is exactly the same thing of a descent datum, but this time to every morphism in the bisieve, we associate a morphism instead of an object, so this W of F. And we still ask compatibility conditions for this W of F with respect to composition. And this time we have, instead of having the phi f g, instead of being invertible morphisms, they are invertible two cells of this form. So we have a bunch of invertible two cells, and this needs to be compatible. So they satisfy a cocycle condition that I'm not showing you, but there is this cocycle condition on morphisms that still relates the two cells that we expect to find. And it still relates them using a natural two cell, a canonical two cell that is given by the fact that F is a triomorphism. But this time we have some extra conditions that we didn't have in dimension one. And the first is that we now have two cells in the bisieve. So the descent datum on morphisms will assign also to every two cell an invertible two cell of this form. And also these two cells are compatible. And we also have additional coherence conditions. And all these conditions are in some sense given by the structure two cells of the three modifications that we have on the right-hand side of the bioequivalence. And so what we get is that the essential surjectivity of morphisms gives the condition that every descent datum of morphisms is effective. And this is again something that we might expect to find, because for a stack, we have that for objects, the condition is every descent datum is effective. And when we go one dimension higher, this same condition shifts to morphisms. So we have that the two stack is such that every descent datum of morphisms is effective. And now we get to the object part, which is the most complicated one, because we don't know what to expect here. We don't have a similar condition for stacks. Okay, we can expect to find a weaker condition than the effectiveness, but we don't know how this should look like. Oh, sorry, I said this, but I didn't. Maybe I didn't say this in detail, so I'll go over it in detail. So a descent datum of morphisms is effective if we can find a morphism W, and for every morphism in the sieve, this time a two cell that relates F star of W and W of F. And this choice of two cells is compatible. So this is exactly the thing we have in dimension one for objects, but this time is seen for morphisms. Okay, now we can go to the object part, which is the most interesting one. And here we have a condition of surjectivity up to equivalence classes of objects. And this gives the conditions that every week descent datum is weakly effective. I call this condition like this. Okay, I have to explain what this means. So a weak descent datum assigns to every morphism in the bisieve an object WF in f of d, and to every pair of composable morphisms an equivalence of this form. So this time phi fg is not invertible anymore. It is just an equivalence. And this is why I call it weak descent datum. And here you can notice that we don't have W of F composed with G, but we have this tilde here. And this tilde means that we consider the morphism isomorphic to F composed with G that is in the bisieve. Because if you remember, we said that the bisieve is not closed under precomposition, but it is up to isomorphism. So every time we have a morphism in the bisieve, in this case F, and we precompose it with another morphism, in this case G, we are not sure to get something in the bisieve, but we know that there is a morphism isomorphic to F composed with G, which is in the bisieve. And we denote it with F composed with G tilde. And then again, since we have a two-dimensional sieve, a bisieve, we need to have an assignment also for every two cell. So for every two cell gamma from F to F prime, we will have a morphism of this form, W gamma between WF and WF prime. And these morphisms are given in a pseudo-functorial way. So they respect, the assignment respects composites and identities up to isomorphisms, at least. And again, we have a cocycle condition, but this cocycle condition is weak in the sense that it is not a commutative diagram anymore. It's not an equality of morphisms, but here we get an invertible two cell. And this time we have two canonical isomorphisms. So the one on the right is given by the fact that F is a triomorphism. So it's similar to the one that we had in dimension one, while the one on the left is given by the fact that the bisieve is not closed under precomposition. And so we need to relate these two objects. And we also have some additional coherence conditions that I'm not showing you, but they are quite natural. And now we say that this weak descent datum is weakly effective if we can find an object W in f of C, and for every morphism in S, an equivalence between WF and F star W. So then this is weakly effective. Instead of an isomorphism, we get an equivalence. And these equivalences are compatible in the sense that if we have F and G composable with the second one in S, we get an invertible two-cell of this form. And so, again, this condition is similar to the weak cocycle condition, but for the equivalences, the psi's equivalences instead of a phi. So this is the condition we get on objects. And so summarizing, the characterization says that a triomorphism is a two-stack if and only if every weak descent datum is weakly effective, every descent datum on morphisms is effective, and F is a sheaf on two cells. And these conditions are quite nice, and they look similar to the ones that we have for a stack. And they are also quite easy to use in practice. And so you might wonder why we cannot give this as a definition of two-stack to begin with. And the problem is that if we want to give a definition of two-stack of this form, we don't know what are the right coherences to ask. So we don't know how to define a weak descent datum or how to define this weakly effectiveness in detail. And so the idea is that our abstract definition guides us in finding the right explicit conditions to ask. And so this is the notion of two-stack. Maybe before we move on to the example of quotient two stacks, if anyone has a question, I'm happy to answer.
Any questions?
Okay, if not, I can.
Maybe I will ask one question. For example, when we define the affine scheme, we consider the sheaf of rings kind of thing. So is there some higher dimensional version?
Yes, so a stack is a higher dimensional version of a sheaf.
Yes.
And the two-stack is a higher dimensional version of a stack. So there are like two steps.
Yeah, but I mean, like, do we have like sheaf of rings kind of thing? Like, is there something called two rings and so on?
Oh, this I don't know. Maybe. I don't
see.
know.
I see. Okay, thank you. Yeah.
Okay, so now I will try to explain why I needed this notion of two-stack, starting from the beginning. So I wanted to generalize to the context of sites the notions of principal bundles and quotient stacks that are notions that are used a lot in geometrical context, in particular for topological spaces or differentiable manifolds. And so I gave a general framework for these notions so that one can use them in any category, in different flavors. So if you know the notion of principal bundle for topological spaces, for example, you might remember that one of the ingredients is the notion of locally trivial morphism, which for topological spaces is something quite natural to define. But in this general case, I needed to define a notion of locally trivial morphism in the site. And the idea is that this time the topological group that we had in the definition of principal G bundle here becomes an internal group in the category. And we say that a morphism of the category is locally trivial if, so this morphism G is locally trivial if there exists a covering family, which is the basis, the other language I mentioned to speak about Grothendieck topologies. You can also think of a sieve instead of a covering family, and it works anyway. So every time we consider a morphism in the site G, and we pull it back along all the morphisms of this covering family, what we get is trivial. And this definition generalizes the usual definition for topological spaces. And now we can say that a principal G bundle over an object X is another object of the category P that has an action of the group object G on it, and the G equivariant locally trivial morphism of this form, pi P from P to X. And we can also define morphisms of principal G bundles in a natural way, so they are just morphisms in the slice category over X. And so this definition generalizes the notion of principal G bundles over topological spaces. In particular, the case of topological spaces can be obtained when the category is the category of topological spaces, and the Grothendieck topology is the standard Grothendieck topology. So the covering families over a topological space are just the usual open coverings of the topological space. So the morphisms are just inclusions. And we get the usual definition of principal bundle. And one interesting thing to notice is that principal G bundles are closed under pullbacks. So if we take a principal G bundle and we pull it back along a morphism, what we get will be a principal G bundle over the source of the morphism. And one interesting thing that one can do with principal G bundles in the classical case of topological spaces is that it can be used to construct quotient stacks and quotient stacks. And we can perform an analogous construction in this generalized case of categories. So if we have an object we fix an object X of the category C and the group object G, the quotient pre-stack X over G is defined in this way. So for every object in the category C, X over G of this object is the category of principal G bundles over the object, all equipped with a G equivariant morphism into the fixed object X. And then for every morphism in C, we define X over G of this morphism simply by a pullback along F. And this really gives a pseudo functor, and the important ingredient of the proof of the fact that this is well defined and gives a pseudo functor is that principal bundles are closed under pullbacks. this is what we need to define these quotient pre-stack homomorphisms in particular. And so what I did is I proved that if the category is nice enough, in particular, this means that it is co-complete and finitely complete, and that pullbacks preserve co-limits. And if the Grothendieck topology is subcanonical, and this means that every representable is a sheaf, and this is a mild condition that is satisfied by almost all the geometric examples of sites, for example, then the quotient pre-stack x over g is a stack, so it satisfies some gluing conditions. And the proof of this theorem was quite complicated, but one of the key ideas that I used in the proof is that every object of a subcanonical site is the co-limit of every covering sieve over it. So we have this property, which is a well-known property of subcanonical sites, and this is really a key ingredient of the proof. And then I wanted to do the same thing, but one dimension higher, and the reason of this is because in some cases, principal G2 bundles are used in higher gauge theory. So they have a lot of applications, and so I wanted to give also the stacky picture of the things. So I moved to dimension 2. So now K will be a 2-1 category with all finite flexible limits. Some of the things that I'm going to say are true for a 2 category. I will maybe tell you where I really need the 2-1 category. And so this time, G is not a group object, but is an internal 2 group in K. And we can easily define what a 2 locally trivial morphism is. So we say that G is 2 locally trivial if we can find a bisieve such that for every morphism in the bisieve, the bi-isocomma object of this form is equivalent to a product G times U. So again, the pullback here is upgraded to a bi-isocomma object, 1 dimension higher. And now we can say that a principal G2 bundle is an object of the 2 category with an action of G on it. And the G equivariant locally trivial morphism, 2 locally trivial morphism, pi p from P to Y. And we can again define a morphism of G2 bundles and the 2 cell of G2 bundles. So so the G2 bundles over an object form a 2 category in this case. And here we have that principal G2 bundles are closed under bi-isocomma objects. And this is a very important result because it allows the construction of the quotient pre-2 stack that we are going to see in a moment. And this is also one of the main motivations for me to choose a bi-topology, because I need the topology to be closed under bi-isocomma objects if I want to prove this result. And so with this in hand, we can define the quotient pre-2 stack X over G that this time is a triomomorphism. And it sends every object of K into the 2 category of principal G2 bundles over the object, equipped with G equivariant morphisms. And then for every morphism, we can define the action of X over G via isocomma object. And we can also define the action on 2 cells using the universal property of the isocomma object. And here, we really need to have a 2-1 category. Otherwise, the this doesn't work. We cannot define the actionomorphisms and two cells if we just have a two category. And so now I add this object, which is quite naturally a higher generalization, a higher version of the quotient stack. But there was no notion of two stacks suitable for this object. And this is why I introduced the notion of two stack that we saw before. And then I managed to prove that if the category, the two category is nice enough, and by nice enough, I mean bico-complete and finitely bicomplete, and such that common objects preserve bico-limits. And if you notice, these are exactly the condition that we had in dimension 1. And if the topology is subcanonical, and here by subcanonical, we mean that every representable is a stack. This is a higher version of the subcanonical Grothendieck topology. Then X over G is a two stack, according to our definition. And actually what I used in the proof was the characterization to prove this result. And here, the key idea of this proof is a higher dimensional version of the idea that we saw for dimension 1. So in dimension 1, we had that every object can be seen as a co-limit of every covering sieve over it. And here I proved that every object of a subcanonical bisite can still be seen as some kind of co-limit of the covering bisieves. And this co-limit is a sigma bicolimit, so it's a two-dimensional co-limit. And so this result is what actually allows me to prove that X over G is a two stack in this context. And this is what I wanted to say. So thank you very much for your attention. If you have questions, feel free to ask. And here you have the references of the talk.
Thank you very much for your very nice talk. I mean, this is also some preparation for your next week's thesis defense, Viva. Yeah. So any questions or comments? So maybe I will ask, you said that the theory that you developed has applications to gauge theory.
Yes, I hope so.
There is this, there was one speaker, his name was Urs Schreiber, a physicist actually, and he uses higher category theory, and I am sure he's interested in gauge theory also. So maybe you get in touch with him. I mean, he will.
Yes. I know some of his papers, not everything, but yeah, thank you.
And also, I will ask one question about, is there a vector bundle version of the second part of your thesis?
I believe there is, but I haven't seen the details.
I see.
Yeah.
Yeah. Thank you. Any more questions or comments? So let's thank our speaker once more and wish her good luck in her Viva. Yeah. So we will meet 2 weeks later. This time, our speaker is from Australia. So our meeting time will be 11 o'clock in the morning. So hope to see all of you 2 weeks from now. So bye-bye.
Bye, thank you.
Oh, you're welcome.